Webb unlocks secrets of one of the most distant galaxies ever seen. Looking deeply into space and time. Two teams using NASA James Webb Space Telescope have studied the exceptionally luminous galaxy, GN-z11, which existed when our 13.8 billion-year-old universe was only about 430 million years old, delivering on its promise to transform our understanding of the early universe. The James Webb Space Telescope is probing galaxies near the dawn of time. One of these is the exceptionally luminous galaxy GN-z11, which existed when the universe was just a tiny fraction of its current age. Initially detected with the NASA and ESA Hubble Space Telescope, it is one of the youngest and most distant galaxies ever observed, and it is also one of the most enigmatic. Why is it so bright? Webb appears to have found the answer. Initially detected with NASA's Hubble Space Telescope, this galaxy, one of the youngest and most distant ever observed, is so bright that it is challenging scientists to understand why. Now, GN-z11 is giving up some of its secrets. Two astronomy research teams have examined space and time in great detail using NASA's James Webb Space Telescope. They discovered the first concrete proof that the bright galaxy GN-z11 is home to a central supermassive black hole that is ICC rating matter at a rapid pace. This is the most distant supermassive black hole observed in the universe. One of the most significant objectives of contemporary astronomy is to locate the previously unseen population II stars. The first generation of stars generated nearly exclusively from hydrogen and helium. These stars are expected to be extremely hot, bright, and huge. Their predicted signatures are the existence of ionized helium and the lack of chemical components heavier than helium. This image from NASA's James Webb Space Telescope NIRCam instrument shows a portion of the Goods North field of galaxies. At lower right, a pullout highlights the galaxy GN-z11, which is seen at a time just 430 million years after the Big Bang. The image reveals an extended component, tracing the GN-z11 host galaxy, and a central compact source whose colors are consistent with those of an accretion disk surrounding a. Using Webb, the team also found indications of ionized chemical elements typically observed near ICC rating supermassive black holes. Additionally, they discovered a very powerful wind being expelled by the galaxy. Such high-velocity winds are typically driven by processes associated with vigorously ICC rating supermassive black holes. Webb's NIRCam has revealed an extended component, tracing the host galaxy, and a central, compact source whose colors are consistent with those of an accretion disk surrounding a black hole, said investigator Hanabi Ler, also of the Cavendish Laboratory and the Kavli Institute. Together, this evidence shows that GN-z11 hosts a 2 million solar mass supermassive black hole in a very active phase of consuming matter, which is why it's so luminous. Pristine gas clump in GN-z11's halo intrigues researchers. A second team, also led by Mayo Luno, used Webb's near-infrared spectrograph to find a gaseous clump of helium in the halo surrounding GN-z11. The fact that we don't see anything else beyond helium suggests that this clump must be fairly pristine, said Mayo Luno. This is something that was expected by theory and simulations in the vicinity of particularly massive galaxies from these epochs, that there should be pockets of pristine gas surviving in the halo, and these may collapse and form population II star clusters. Finding the never-before-seen population II stars, the first generation of stars formed almost entirely from hydrogen and helium, is one of the most important goals of modern astrophysics. These stars are anticipated to be very massive, very luminous, and very hot. Their expected signature is the presence of ionized helium and the absence of chemical elements heavier than helium. The formation of the first stars and galaxies marks a fundamental shift in cosmic history, during which the universe evolved from a dark and relatively simple state into the highly structured and complex environment we see today. This two-part graphic shows evidence of a gaseous clump of helium in the halo surrounding Galaxy GN-z11. In the top portion, at the far right, a small box identifies GN-z11 in a field of galaxies. The middle box shows a zoomed-in image of the galaxy. The box at the far left displays a map of the helium gas in the halo of GN-z11, including a clump that does not appear in the infrared colors shown in the middle panel. In the lower half of the graphic, a spectrum shows the distinct fingerprint of helium in the halo. The full spectrum shows no evidence of other elements and so suggests that the helium clump must be fairly pristine, made of hydrogen and helium gas left over from the Big Bang, without much contamination from heavier elements produced by stars. Theory and simulations in the vicinity of particularly massive galaxies from these epochs predict that there should be pockets of pristine gas surviving in the halo, and these may collapse and form population II star clusters. The discovery of pristine gas clumps in the halo of GN-z11 underscores the complex interplay between galactic dynamics and the formation of primordial stars, representing a pivotal milestone in unraveling the mysteries of cosmic evolution. The James Webb Space Telescope JWST is a space telescope designed to conduct infrared astronomy. Its high-resolution and high-sensitivity instruments allow it to view objects too old, distant, or faint for the Hubble Space Telescope. This enables investigations across many fields of astronomy and cosmology, such as observation of the first stars and the formation of the first galaxies, and detailed atmospheric characterization of potentially habitable exoplanets. The James Webb Space Telescope is an international project led by NASA in partnership with ESA and the Canadian Space Agency, in addition to providing the Ariane 5 rocket and launch services to bring the telescope into space. ESA is also providing instruments for the telescope as well as scientists who will support the mission's operations. This includes the NIR-SPEC instrument, the workhorse near-infrared spectrograph on board Webb, which is provided entirely by ESA. The primary goal of NIR-SPEC is to enable large spectroscopic surveys of astronomical objects, such as stars or distant galaxies. This is made possible by its powerful multi-object spectroscopy mode. ESA is also supporting the provision of the MIRI instrument, the only instrument on the telescope that is capable of operating at mid-infrared wavelengths. It will support the whole range of Webb's science goals, from observing our own solar system and other planetary systems, to studying the early universe. MIRI is a versatile instrument offering a wide set of modes. Webb will observe the universe at wavelengths longer than visible light, namely in the near-infrared and mid-infrared, compared to Hubble's 2.4-meter primary mirror. Webb is equipped with a primary mirror that spans 6.5 meters in diameter. Another key difference between Hubble and Webb is where they are located to study the cosmos. While Hubble is positioned in Earth orbit at an altitude of approximately 570 kilometers, Webb will be orbiting a point in space beyond the orbit of the Moon known as a Lagrange point, roughly 1.5 million kilometers from Earth. Accessible to the worldwide scientific community, JWST offers scientists the opportunity to observe galaxy evolution, the formation of stars and planets, exoplanetary systems, and our own solar system in ways never before possible. This website offers scientists information on proposing for time on JWST as well as the capabilities of the observatory's instruments and modes, data analysis tools and software, and news and events.